All right, for this third lesson looking at population tests, your focus is on what we call a type 1 or a type 2 error. And for a lot of this lesson, it is to be expected that you'll probably find elements of it quite challenging. That is at least to be expected. In general, though, what is not so challenging is what a type 1 or a type 2 error is. Sometimes, we have a null hypothesis, and sometimes we reject it because we come up with some statistical measure and we determine, based on the significance level perhaps, that we need to reject it. But there is a chance that it's actually true. Just because something falls within is less than the significance percentage and the probability is less than perhaps 5%, doesn't mean it is for sure incorrect. It's just it falls within our critical region, and so we reject it. And so a type 1 error is when we reject H naught, even though it's actually true. And as we'll see, those are generally a little easier to deal with. The other one is the other way around. A type 2 error is when we don't reject H naught, even though we actually should reject it, when it's actually false. So first, let's focus on a type 1 error, which again, we'll see is going to be a bit easier to work with. And in general, it's when we reject H naught, we accept the alternative hypothesis, although perhaps later on we discover that was wrong, which is something we got to realize. There's always a chance we're wrong with statistics. Now, if I look at this first example, I have some normal distribution. I don't know what the mean is, but I know there is a variance of 4. And we want to conduct a hypothesis test with a 10% significance level with a sample size of 15. And our null hypothesis is that the mean is 6. Our alternative hypothesis is that the mean is not 6. What's the probability that we can conduct this test and make a type 1 error, which means what's the probability that we might reject the null hypothesis even though it was actually correct? In this case, it's going to be quite easy. In general, when we have a continuous distribution, and a normal distribution is a continuous distribution, then the probability of making a type 1 error is the exact same as our significance level. If we just think about what a normal distribution looks like. All right, and in this case, I don't even need to, we have our mean here, but all that really matters is that 10% significance level. In this case, is this region here or this region here? Because keep in mind, we are looking at the alternative hypothesis being that the mean is not 6. So I guess I'll put a 6 there. And so these two regions together, if it turns out that our probability is within either of those two regions, then we are in a critical region, which means we should reject our null hypothesis. And so in this case, because it is 10% altogether, again, this is a two-tailed test. That means this is 0.05 in area, this is 0.05 in area. Put all together, it's 10% of the entire area. And so the probability of us making this mistake is 10%. And so there is a 10% chance of making a type 1 error. So notice in this question, once we realized it was a normal distribution, nothing else actually mattered except the significance level. The fact the mean was 6 or not 6, the fact that it was a two-tailed critical region or not, didn't actually matter. All that mattered is if there's a 10% significance level, there is a 10% chance that we are going to be wrong in the end from our judgment. With that said, what's more challenging is if we don't have a normal distribution. So I have a binomial distribution. So here, these values are a bit more important. Binomial distribution with 8 trials and an unknown probability. But our hypothesis test is that the null hypothesis is that the probability is 1/3. Our alternative hypothesis is that the probability is more than 1/3. However, this time, instead of being given a significance region as a percentage, we've been just given the critical region as any value greater than or equal to 6. So I'm going to visualize, again, a distribution. Now, a binomial distribution, keep in mind, is not continuous. It's actually a bunch of steps, but it has a sort of rough shape as a normal distribution, but it is finite. And so just keep in mind, all these little curves are actually steps. It's finite. The mean, in this case, is always in the middle. And for this, we know the critical region is everything more than 6. And so I'll just kind of draw a little 6 here. And so this is our critical region right here. And so, which again is everything greater than or equal to 6. So we want to find what's the probability that a result will end up being greater than or equal to 6, assuming the probability really is 1/3. And so I want to find the probability of x being greater than or equal to 6. And that's it on most GDCs. You can't calculate this exactly, so I want to do the complement. I want to go 1 minus the probability of x being less than 6. Although keep in mind, because this is a discrete distribution, being less than 6 means being less than or equal to 5. So instead of writing less than 6, I'll write less than or equal to 5. With that said, this is now pretty quick. I can go to my GDC with, again, use the binomial cumulative distribution function for this part right here, with 8 trials and a probability of 1/3. Again, going back to our null hypothesis, and we should get about 1 minus 0.980, or approximately about 0.0200, which is about a 2% probability, which means if this probability of success is correct, there is a 2% probability that we will reject that null hypothesis even though it's correct, because there's a 2% probability that our results will end up in that small critical region. Just a 2% probability. All right, just keep in mind before we go on to type 2 errors. A type 1 error, like I said, if you have a normal distribution, it is the exact same percentage. If it's not, it is going to be related to it. All right, type 2 errors are the other way around. When we end up rejecting, we don't reject, if I just look at the writing right here, we don't reject H naught, but we actually should reject it. It actually is false. So the other way around. These will be a bit more work to think about. So here I'm going back to my first distribution that for a type 1 error was quite quick. The probability of a type 1 error is 10%. But what's the probability of a type 2 error? All right, so first, now I got to look at these features a bit more. So we don't know the mean, but we're testing our null hypothesis that the mean is 6. Our alternative hypothesis, again, is the mean is not 6. So I'm going to go back to my same sort of visual I had before. I'm going to draw this normal distribution. Again, we have 6 here. In this case, again, since we just want to see that the mean is not 6, we have 2 critical regions that are symmetrical over here and over here. And keep in mind, like I mentioned before, each of these is 5% of the total area, or 0.05 is a decimal. So what I first want to do is figure, okay, what is this value right here, and what is this value right here? What are the critical values for this, in this case, this two-tailed, these 2 critical regions? And since we are looking at a sample, we are going to go with our null hypothesis of the mean being 6, but the variance, keep in mind, that is for the whole population. We're looking at a sample of 15. So we got to keep in mind for this that while our mean we are going to use as 6, the standard deviation is going to be the square root of the variance, which will be 4 divided by the sample size, or in this case, 2 over root 15. And that's what I want to use for this. And to find these 2 values here, we now want to use our GDC and use the inverse normal function. So inverse normal. And depending on your GDC, you may have to break it up into 2 parts and first find what's the probability of just this region here, or left-tailed at 5%, or an area of 0.05, and then separately find the probability of, or the x value that would have an area of 0.05 to the right, or some GDCs like the T84, you can find the area that would be the center. Lots of ways of approaching it. In the end, though, you should get 2 values. So if we do it by the 2 different tails, for the left tail, you should get approximately 5.1506. And again, that's looking at the area of 0.05. So this question mark here is approximately, this critical value is approximately 5.15. And the other one, this side for the right tail, that area of 0.05, that should come to about 6.85. I'll write 6.85 here. I'll put a few more significant figures down here. So a few more significant figures. I got 6.8494. And again, that refers to that area of 0.05, or again, if you can, just find the region in the center, if you use the inverse, if your calculator can. This area in the center that I'm highlighting in green is 90%, and you should get the same two values. Depends on your GDC. So now we want to do, those are the critical values, assuming our null hypothesis is true. But what if we then determine that it looks like that our null hypothesis is wrong, but we don't realize it? What if the mean was actually 7.5? What is the probability that we'll miss that? And so what we need to do next is make a new distribution. This time, it's still a normal distribution, so same rough sort of shape, but this time looking at our new mean of 7.5. But now we want to think, okay, what is the probability that we would get, with this mean, we would get a value between these two critical regions? Because remember, if we get a value between these two critical values, I should say, then we reject our null hypothesis. But keep in mind, what we don't realize is that we really should be rejecting. If we get something within here, we don't reject our null hypothesis. Yet if the mean actually is 7.5, we should reject it. So what is the probability of this happening? And so at this point, I look at a new distribution. Again, the mean is 7.5. But I now think about where would those critical values, 5.15 and 6.85, where would they be on this? And so they're both to the left of the mean. So I'll just sketch this roughly. So 5.15 is here, let's say 6.85 is here. And so now we need to figure out, okay, what's the probability, if the mean really is 7.5, of getting a sample mean or getting a value within that region there? And so now the hardest part is done, because I have everything set up. And again, I want to use my normal function, but this time I know the bounds of it, so I can just use our normal cumulative distribution function, in which we want to find the probability with a mean of 7.5 and a variance, again, of 2 over root 15. But this time, what's the probability of it being between these two bounds? So, and I would actually use these values down here, which are more accurate. If you do that, you should pretty quickly get to a probability of about 0.104, which is approximately 10.4%, which means we have a 10.4% chance of making a type 2 error. Helps if I can spell. Which, keep in mind, means in this point, there's a 10% chance, if the mean really is 7.5, there's a 10% chance that we will keep our null hypothesis, just based on what we get from our sample, that we will not reject our null hypothesis, even though we really should have, because if the mean is 7.5, we should be rejecting it. There's a 10% chance of making that error, which again is a type 2 error. So before we go on to the last question, just keep in mind this type 2 error question was significantly more work than this type 1 error question for the exact same setup. All right, lastly, we have a Poisson distribution question here, in which we have looking at statistics about how busy a subway is. And so on weekday afternoons, a train passes a station in Bangkok every 10 minutes. The subway authority has decided to keep trains at this rate unless the number of people waiting for a train becomes an average greater than 50 between two trains. All right, so I'll keep reading a bit more. On a certain afternoon, a subway employee has been asked to count the number of people waiting for a train over the course of an hour. So this is where I'm going to pause. The information before was in minutes, and so we had 50 people between trains, and trains came every 10 minutes. So that leads us to 50, every 10 minutes. That means 6 times an hour is a train, so times this by 6. So that means we can say on average there are 300 people waiting at the train station, because we want to scale everything up to a common sort of time frame. And everything's going to be in terms of hours after this, because the employee has been asked to count the number of passengers in 1 hour. The total number of people will then be used to carry out a hypothesis test at a 5% significance level. The subway authority then carries out this test and wants to determine whether or not they should increase the number of trains. All right, so by considering the critical value, we want to calculate the probability of making a type 2 error, given that the actual mean is 335 in 1 hour. So lots to unpack here. I've already done a little bit. Let's first start with that 300 people. And so 300 people an hour, that is the assumed mean. So that is our null hypothesis. So H naught is that the mean is 50 times 6, or 300 people per hour. Which means our alternative hypothesis is that the mean is going to be more than 300. Because in this case, we're not really concerned if it's less busy. We're trying to figure out if they need to run more trains. Which again, they will run more trains unless the number of people waiting for a train becomes greater than that. So all we care is if it's greater than 50 between 2 trains, or an hour more than 300. All right, so we know we have a 5% significance level. So let's actually find, like in the last question, let's find the critical values for the significance level. In the last question, it was a two-tailed critical region. Here is just going to be 1. It's just greater than. And I'm going to make a quick little visual here again of our Poisson distribution, which is related to a binomial distribution, which is similar to a normal distribution. So it has the same sort of rough bell curve-ish shape. And we're going to go with our null hypothesis, which is saying this is 300. And we need to find the critical region. And the critical region will be 5% of the total area, but more than the mean. And so I'll just kind of sketch it. It's something like here. So we want this region to be to a maximum of 5%, or 0.05. The question is, again, where is this region? So up here, when we had something similar, we could use our inverse normal function, but a lot of GDCs don't have an inverse Poisson function. So what we want to do is, as we've seen in previous lessons, we probably want to either use our graphing device with either graphing, or, as I'd recommend from previous lessons, use a table. And so let's use our Poisson cumulative distribution function, in which the mean is 300, but the x value is x. We don't know. And we know it's going to be something more than 300. So when I go to my table, I want to set it up so that I'm looking at values past 300, because it's going to be somewhere more than 300. And what we're really trying to figure out is what's the probability, and maybe I should actually state right here more formally that x is a random variable from a Poisson distribution with a mean of 300. So that's my x. I want to find what's the probability that x is greater than or equal to some number, I'm trying to figure that out, such that this probability becomes less than or equal to 5%. So that's what we're really trying to figure out. Now, keep in mind again, if we use the Poisson cumulative distribution function, it allows us to find not where values are greater than, but less than or equal to. And so we want to, if I do something like this, if you look at your table, I want to graph actually 1 minus the Poisson cumulative distribution function for 300 comma x. Look at your table and you'll see values like this. For example, when x is 328, which means 1 minus the probability of x being less than or equal to 328, you'll see is approximately 0.0516. If you look at the next row in the table, when x is 329, which means if we're graphing 1 minus this is the probability of 1 minus the probability of x being less than or equal to 329. That is approximately 0.0459. We have now reached, for the first time, the region where our probability is less than 5%. But remember, I want to think about where x is greater than or equal to some value. I found where 1 minus probability of x is less than or equal to 329. So what does that mean? Well, remember, being less than or equal to 329 means 329, 328, 327, all the way down. But 1 minus that means everything else. So that means everything that is not 329, 328, and everything below, which means this is equivalent to the probability of x being greater than or equal to 330. And we saw similar things in 459. I can't read my own writing here. So these two expressions here are equivalent, and we saw similar things in previous lessons, which means this here is our critical value. Because when x is at 330 or more, which keep in mind this question means when there are 330 or more people waiting for a train in an hour, according to this, we should actually reject our null hypothesis, and we should accept the alternative one, which means we should run more trains. All right, so I can now go back to my visual here, change that question mark, and put it as 330. That is our critical value. Which, keep in mind, again, has to be a whole number. So if there's 330 or more, according to this, we should reject this and accept this. All right, but there's a probability that, depending on the sample, that we'll get this wrong. And so now if we look back up here, once we found our critical regions, we now look at a new distribution using our updated information about the mean. In this case, what if the mean is actually 335? So I'll make another distribution here. Right? So what if the mean is actually 335? What's the probability that we will fall outside of the critical region even though we have rejected this? And so we know our critical region starts at 330, which I know is to the left of this, 330, which means our critical region is all of this, okay? But we want to find the probability that it ends up in here. Same thing up here. We want to find the probability. All of this up here was the critical region now, but we want to find the probability of being outside the critical region. So what is the probability with a Poisson distribution with this particular mean of 335 of it ending up in the region less than 330? This is now quite quick. So we have a new distribution, Poisson distribution of 335, and we want to find the Poisson cumulative distribution function to determine where the probability of x is less than or equal to 329. Again, 330 is the beginning of our critical region. So from there onwards, we're in the critical region. We want to find what's the probability of being outside the critical region, hence from 329 or less. And that is extremely quick and easy to do on a GDC. It's pretty direct. You should get approximately 0.385, which means approximately a 38.5% probability of making a type 2 error. Which means if the mean number of people waiting at the this train station is on average normally 335, there is a 38.5% chance that because of the sample that someone will not think there's a need to run more trains, even though we really should, because remember, everything over 330, we should run more trains. And so there's a 38.5% chance that the subway authority will not think it needs to run more trains, even though it should, because the mean is 335. And that's all comes down to the fact that just by random chance, the sample that this person took just happened to be on the low end. And so we always got to keep in mind, a sample is a sample, and there's a variation in the samples, and there's always a chance for errors. And there's no way around that. All right, finally, just to kind of finish things off, if it seems kind of annoying that there's always this probability, this chance of an error with statistics, well, such is life in general. If you want to reduce the probability of a type 1 error, then that's not hard to do. If you want to reduce the probability of a type 1 error, you reduce your significance level. The smaller you make your significance level, the less and less of a chance there is of making a type 1 error. But that then brings us to the bigger chance of making a type 2 error, and vice versa. The larger your significance error level is, the greater chance you'll make one of those errors. So in the end, there's always the possibility. We just want to be able to calculate the probability of making such an error. And remember, I said from the start, this is probably one of the more challenging lessons. Maybe you agree with me. Maybe